Lesson 14. Inductance. Section 14.1. Self-inductance. This is an electric circuit. A current source of I amperes is connected to a circular conductor. The current flows through the loop. A magnetic flux of density of B teslas is generated by the current I. Define the flux linkage phi as positive when B is in this direction. If the current I is increasing, then the derivative of the flux linkage phi is positive. The counter-electromotive force Vc, which opposes the increasing flux, becomes positive. This is the definition of self-inductance L. The self-inductance L is the coefficient relating the flux linkage N phi and the current I. The unit is Henry. Note that the direction of the flux is opposite to that in the previous lesson. Faraday's law was introduced with the opposite direction of phi. This difference in the polarity is due to the different purposes for which these equations are used. Inductance L may be defined as the coefficient relating the applied voltage V to the derivative of the current I. This is the symbol for an inductor, along with the definitions of the polarities for the applied voltage V and current I. Exercise 14.1.1. Pause the video, and answer the problem. Find the counter-electromotive force Vc. The answer to exercise 14.1.1. Pause the video and check the answer. Exercise 14.1.2. Pause the video, and answer the problem. Find the self-inductance of the two conductors per unit length. The answer to exercise 14.1.2. This is a rectangular conductor. A current I flows clockwise through the conductor. A magnetic flux density B is generated by the current and passes through the surface S bounded by the conductor. The flux linkage is the area integral of B over S. We can extend the upper and lower sides of the rectangular conductor to infinity for exercise 14.1.2. Based on this viewpoint on the inductance between two line conductors, we can derive the inductance per unit length. A distance of R meters is defined from the center of the left-hand side conductor. According to exercise 10.2.1, the magnetic field intensity H is given by this equation. Then the magnetic flux density B is derived by multiplying H by mu. By defining a differential distance dr, we can obtain the differential flux d phi passing through the differential area using this equation. The flux phi, passing through the area between the two conductors per unit length, is obtained by integrating d phi from R1 to R2. Note that the range of integration does not start from 0, because the flux linkage within the conductor, ranging from 0 to R1, differs from the flux linkage described above. The range of integration stops at the center of the right-hand side conductor R2. This is acceptable based on the theory of geometric mean distance. This theory is left for future study. The total flux linkage phi total is doubled when considering the current flowing in the right-hand conductor. Hence, the inductance outside the conductor per unit length is derived as shown in this equation. Next, let's take a look inside the conductor on the left-hand side. It is assumed that the current I is uniform throughout the conductor. According to exercise 10.2.2, H at a distance R is given by this equation. the differential flux d phi through the differential area is given by this equation. For the external conductor, the number of turns n is multiplied onto the flux phi, because n times I amperes are linked to the flux. For the internal conductor, the current inside the radius r is linked to the differential phi. Thus, n equivalent n is the ratio of the cross-sectional areas. The flux linkage phi inside the conductor per unit length is independent of the radius of conductor. Therefore, the internal inductance per unit length is derived as shown in this equation. This is the answer to exercise 14.1.2. The internal inductance is doubled for both sides of the conductors. Exercise 14.1.3. Pause the video, and answer the problem. The answer to exercise 14.1.3. Pause the video, and check the answer. The author of this material is Takeshi Furuhashi, Professor Emeritus, Nagoya University. If you have any questions, send emails to this address.